Okay, so this is the class for Thursday, April 16th, and we're going to start talking about quantitative variables. So this is back to chapter 8, talking about analysis where we're estimating one mean. So up until now in our stat stuff, we've always done cases where the information we were collecting was categorical, and basically like a multiple choice question. At first, we sort of focused on what proportion gave a particular answer. And then just now with the chi-squared test, we allowed for multiple different answers in our analysis. So now we're going to shift to questions where people's answer, the piece of information we're collecting is a number. So we're going to have quantitative or numerical data instead. So let's just jump straight in with an example. So in our first example, we grow 10 bean plants and we measure the pounds produced by each plant. So I'm gonna just list the numbers that we got. So we're gonna have actual data here. So the first had 1.8 pounds, then 1.5, 1.4, 2.1, 0.6, 1.5, 1.6, 2.0, 1.5, and 1.4. Now, notice those numbers are not in any kind of order, like increasing order. Presumably, they are in the order that they were recorded. So just like we went through the plants one at a time, and this just happens to be the order that the numbers were listed. Okay, so what I want to know is, what is the mean? How much can I expect from a typical bean plant? Now, I can easily find the mean of these 10 numbers. Just, add up all 10 and then divide by 10 and see what we get. But what I really would like to know is, say, well, this is all random, right? Presumably these all came from the same type of soil with the same type of pests attacking them and the same type of nutrients in the soil, fertilizer, and so on. So why are the numbers different? Well, some amount luck, some amount like maybe one seed just happened to produce a stronger plant than another. I want to know if for all of the bean plants that I could possibly grow, what would be the mean? Now, I guess in future years, the weather might be different or something like that. But based on these 10 plants from this particular season, what would be the mean production for all bean plants that I could have possibly grown? So I can get a good guess by just averaging these 10 numbers. But the real answer, which I don't know, could be higher if these just happen to have more bad plants than normal, or it could be lower if this group happened to have more good plants than normal. And we could also get an idea of how accurate our guess is by the standard deviation in these numbers. So these numbers, except for this sort of 0.6 here, these numbers are all between 1.4 and 2.1. There's a fairly tight range there. And so maybe you could think that since 9 out of 10 plants are in that range, maybe that's typically where they fall, and the average for all bean plants should at least be somewhere in that range. So my point is that it makes sense to take into account the standard deviation when you decide how accurate our guess is. If our first guess is just the mean of our sample, we want to know how accurate that guess is, like how wide our confidence interval has to be. The standard deviation should take that into account. So our first guess for the population mean, so that's the mean of all possible bean plants that were in this situation, is to just find the sample mean. And we're going to have a symbol for the population mean. We're going to use the letter mu, the Greek letter mu, that I often used for mean earlier in the semester. So I think I need to bring up my Greek letters for mu. No, I don't. It's right there. And the sample mean, what we're going to use for sample mean is an x with a bar over top. I think maybe I've used that before. I'm not sure if I used bar over top for a mean before, but that's a pretty typical notation to stick a bar over top of a letter or something like that to indicate that you're taking the mean. So there's our bar. Oops. Somehow that got a vector over top. I think when my computer gave that announcement, I misclicked. Okay, so x with a bar over top. To just take the sample mean. Okay, so so we can add up those 10 numbers and divide by 10 and see what we get. So I haven't done that ahead of time. I'm going to have Minitab do all of this in a second. We could also find the standard deviation for our sample. Could find the standard deviation for our sample, which we're going to use just the letter S for the sample standard deviation. Now, I'm sure there's ways that you could estimate the standard deviation for the population for all bean plants, but we never bother doing that in this class. All of our work is going to be focused on just trying to estimate the mean and not the other thing, not other things like the standard deviation. So this is the standard deviation for like how spread out the bean plants are, but there's another kind of standard deviation, which is how far off we think that our guess is from the real answer. So that's sort of the standard deviation in as you sort of randomly select 10 plants at a time and take their mean, the results are going to bounce around. So the standard deviation for that, we should have a different name for that. We'll call that the standard error. So the standard error, which is the standard deviation for how much the mean of a random sample can vary. So we just have a random sample of 10 bean plants, and it could go up and down some amount. We're calling that the standard error. So that is given by, we're going to have a formula for that. So it is given by the formula. Here, let me zoom in a bit. There's no reason this has to be so small. So that is given by the formula. We're going to use SE for standard error. In the numerator, there's our sample standard deviation S. And in the denominator, there's the square root of the sample size. So that might sound familiar from the proportion section. We also had a square root of n in the denominator for the standard deviation when we were back in our first stat chapter. The numerator had a square root of p times 1 minus p. This time, the numerator is just the sample standard deviation. Okay, so then what I would like to do is let's find a 95% confidence interval for bean, for like the mean bean production. Okay. I think that I'll put the mini tab for this in a second video. So let me stop this video and we'll move on to the second video.